Hello, what is virtualization? That's a great question given that we use virtualization every day when we access the cloud and cloud services. Welcome to the module on virtualization. Click on Start to begin. What's inside? Facade. It's all about understanding virtualization with a real-world analogy and brief definition by different standards. Evolution. It focuses on the journey of virtualization solution. Concepts. A quick glance on what is virtualization, why we go for virtualization, the impact of virtualization on a data center and the terminologies. Approaches. Focuses on the different virtualization approaches like para-virtualization, full and hardware-assisted full virtualization. We have a detailed look on the type of hypervisors like bare metal and hosted hypervisors. Models. The different server virtualization models like processor, memory, input, output virtualization. Types. The different virtualization types like application, server, storage, network, and desktop virtualization. Tools. We have a look on the popular virtualization tools, both open source and proprietary. Some of the abbreviations and acronyms are as follows. OS. Operating System. VM. Virtual Machine. VMM. Virtual Machine Monitor. QEMU. Quit Emulator. CPU. Central Processing Unit. RAM. Random Access Memory. NIC. Network Interface Card. VTX. Virtualization Technology for x86 Architecture. VTI. Virtualization Technology for Itanium Architecture. VTD. Virtualization Technology for Directed I/O. VTC. Virtualization Technology for Connectivity. VMX. Virtual Machine Extension. MMU. Memory Management Unit. I/O. Input, Output. EPT. Extended Page Table. DMA. Direct Memory Access. SAN. Storage Area Network. PCI. Peripheral Component Interconnect. SRIOV. Single Root Input, Output Virtualization. LXC. Linux Containers. KVM. Kernel Virtual Machine. RHEV. Red Hat Enterprise Virtualization. VMware ESXi. VMware Elastic Sky Xi Integrated. KSM. Kernel Same Page Merging. Facade. effective utilization of the living space. Consider a real-world analogy. Building an individual house for a single family in a specific floor area is like a single application running on a server, whereas virtualization is a building apartment to in-house multiple families. Definition: virtualization is the process of running a virtual instance of a computer system in a layer abstracted from the actual hardware. Virtualization is a technology that allows to create multiple emulated environments, dedicated resources from a single physical hardware system. Now, let's explore emulation versus virtualization. Emulation software aims to run a program designed for one kind of system on another system. The programs that make this happen are known as emulators. An emulator is a complete replication of another system, right down to being binary compatible with the emulated system's input and output. Emulator requires a software bridge, like interpreter, that translates the source code into host system's readable format to process it. Now, we can observe few differences between emulation versus virtualization. When it comes to emulation versus virtualization, emulation is a working simulator of a real device, whereas virtualization creates virtual versions of servers, storage, and network devices. Emulation simply allows us to run software from totally different devices on our computer. But virtualization simply allows us to use the complete capacity of physical machines by distributing its capabilities among different environments or users. Emulation usually requires a software bridge to access hardware. But virtualization can access the hardware directly. Emulation is more cost-effective and provides less effective backup solutions as compared to virtualization. Emulation is unnecessarily slower than virtualization. The journey. Virtualization technology was not widely adopted until the early 2000s. In the late 1960s and early 1970s, when IBM invested a lot of time and effort in developing robust time-sharing solutions, which isolated users within operating systems inadvertently, leading to other operating systems like Unix, Linux. This represented a major breakthrough in computer technology. In the mid-1960s, IBM's Cambridge Scientific Center developed CP40, the first version of CMAs, intended to implement full virtualization solution. IBM changed direction and also announced several virtual storage operating systems, including VM 370, time-sharing applications, virtual memory. In 1980, Multi-CS, Unix, Virtual Operating System, Desktop Computing, x86 servers. In 1990, Sun Microsystem, Java, World Wide Web, Java Virtual Machine. In 1998, VMware introduced the first x86 virtualization product, VMware Virtual Platform. VMware Workstation with Software Emulator. Apple Virtual PC. In 2000s, VMware came with their ESX bare metal. Microsoft with their Hyper-V, and Citrix with their Zen solution. Let's have a deeper dive into what is virtualization. In simple words, virtualization is making one computer act like many computers. Every computer has many hardware components: CPU, memory, hard drive, network adapters, and so on. So, virtualization works like this. Take a big computer with plenty of processing memory, storage, and network capacity. Install a piece of software called hypervisor. Hypervisor is the abstraction layer because it abstracts the core computing devices and runs on the physical layer. Hypervisors are also known as Virtual Machine Manager, Virtual Machine Monitor, or Virtualization Manager. This physical machine is called the host. The hypervisor manages the physical resources of the host so that the virtual machines can use them as they need. Guest computers called virtual machines run inside the physical hardware. They act exactly as though they were physical machines. But they are not. They are just big files. Virtualization concepts. Virtualization is separating your OS from underlying hardware. Thus, you can have one kind of hardware architecture, but you can install multiple operating systems on the same hardware system. So, the hardware that you bought is not going to be bound to one and only one operating system. This provides efficient use of resources like processor, memory, storage, and networking hardware components. This optimization of resources reduces cost. Traditionally, you would have one hardware server, then install one operating system, and then install your applications that are compatible with the underlying OS. Now, with virtualization, you buy big hardware, install hypervisor software, then create multiple operating system instances like Windows, Linux, macOS, and so on. And then you can install multiple apps on those operating systems. And all these heterogeneous applications can run simultaneously. Why do we need virtualization? It's simple. It saves memory and resources. Virtualization provides us better utilization of the hardware resources, greater efficiencies in power consumption, physical space, and energy use. It offers us the flexibility to run heterogeneous environments of different architectures, different operating systems like Windows, Linux. As there is a drastic reduction in the hardware resources, managing VMs is much easier than physical resources. Virtual machines are completely isolated and hence provide more security. We are able to isolate our applications better. Since only one hardware server runs for many operating systems, our power requirement is reduced and hence it offers the ultimate reduction in the ownership cost. Managing VMs are much easier than physical resources. Virtualization impact on data center. We shall see the impact benefits of virtualization on a data center. When you bring virtual resources into the data center, it can have a wide-ranging effect on the network infrastructure. Number 1. Less heat buildup. Millions of dollars have gone into the research and design of heat dissipation and control in the data center. But the cold, hard fact is all of those servers generate heat. The only way around that: use fewer servers. How do we manage that? Virtualization. Use less physical hardware and hence we generate less heat. Number 2. Reduced cost. Reduce the amount of hardware used and thereby reduce the cost. But the cost goes well beyond that of hardware, lack of downtime, easier maintenance, less electricity used. Over time, this all adds up. to a significant cost savings. Number 3. Faster redeploy. By encapsulating and abstracting applications from the physical hardware, we create virtual machines, VMs, that are easier to manage, are portable, and can be implemented on physical hardware in seconds. Number 4. Easier backups or snapshots. Not only can we take full backups of our virtual server, we can do backups and snapshots of our virtual machines. These virtual machines can be moved from one server to another and redeployed easier and faster. Snapshots can be taken throughout the day, ensuring much more up-to-date data. Snapshots can be full and incremental. Number 5. Better testing environment. What better testing environment is there than a virtual one? If we make a tragic mistake, all is not lost. Just revert to a previous snapshot and we can move forward as if the mistake didn't even happen. We can also isolate these testing environments from end users while still keeping them online. Number 6. Better disaster recovery. A well-managed virtual infrastructure can provide a high level of fault tolerance for both VMs and virtual applications. Workloads, virtualized storage, and entire VMs can be automatically relocated when network problems arise. Using virtualization usually speeds recovery in the event of a disaster. Number 7. Application isolation. As each application can be hosted in each virtual machines, it offers complete isolation. Number 8. No vendor lock-in. As virtualization is the abstraction between software and hardware, it doesn't have to be tied down to one particular vendor. The virtual machines don't really care what hardware they run on. So, we are not tied down to a single vendor, type of server, or even platform. Number 9. Green pastures. Reducing the carbon footprint from the servers helps to clean up the air we breathe. Number 10. Easier migration to cloud. With a move to virtual machines, we are much closer to enjoying a full-blown cloud environment. We can deploy VMs to and from the data center to create a powerful cloud-based infrastructure. Here are the virtualization terminologies. Let's learn more about each virtualization terminology one by one. Hypervisor or VMM. It is a software program that allows multiple operating systems, VMs, to share a single hardware host. Virtual machine. A virtual machine, VM, is a virtual environment that functions as a virtual computer system with its own CPU, memory, network interface, and storage created on a physical hardware system. Host OS, the physical server equipped with hypervisor like KVM, Hyper-V, and VMware that hosts the VM. Guest OS. It is an operating system that runs under the control of a VMM rather than directly on the hardware. System calls. System calls are programs that request services from the kernel of the OS. It provides the interface between the application or process and the OS. It is a software trap from an application to the kernel. System trap. Exception or fault that switches to kernel mode by invoking any system call. High availability. It is a component of a technology system that eliminates single points of failure to ensure continuous operations or uptime for an extended period. Hypercalls. LT is a software trap from a domain to the hypervisor, whereas the domain is a privileged Linux host OS to access the hardware. Kernel mode. In this mode, the executing code has complete and unrestricted access to the underlying hardware. It can execute any CPU instruction and reference any memory address. User mode. In this mode, the executing code has no ability to directly access hardware or reference memory. Code running in user mode must delegate to system APIs to access hardware or memory. Privileged instructions. An instruction, usually in machine code, that can be executed only by the operating system in a specific mode. For example, set value of timer, clear memory, turn off interrupts, modify entries in device status table, access input-output device. Sensitive instructions. Control-sensitive instructions seek to change the configuration of resources. Behavior-sensitive instructions have different behaviors depending on the configuration of resources, including the load and store operations, the virtual memory. VN cluster. Effective technique to ensure high availability of servers and network to protect resources from failure. Memory Management Unit, MMU. An input-output memory management feature that remaps input-output DMA transfers and device interrupts. Direct Memory Access, DMA. It is a feature of computer systems that allows certain hardware subsystems to access main system RAM independently of the CPU. Input-output virtualization. It is a software technology that abstracts the upper layer protocols from physical connections or physical transports. Digital workspace. A digital workspace is an integrated technology framework designed to deliver and manage app data and desktop delivery. Microkernel. A kernel type that provides low-level address space, thread management, and inter-process communication to implement OS. Monolithic kernel. A kernel type where the entire OS works in the kernel space. Virtual. A virtualization standard for network and disk device drivers aware of being virtualized. It is an abstraction layer over para-virtualized hypervisor. Kernel same-page merging (KSM). It enables KVM guests to share identical memory pages. These shared pages are usually common libraries or other identical high-use data. KSM avoids memory duplication. Machine emulator. QEMU uses binary translation for guest OS. Virtualizer. QEMU achieves near-native performance by executing the guest code directly on the host CPU, like in KVM and Gen. Virtualization components. In general, the hard disk and memory of the physical resources are mapped to the virtual resource, whereas the CPU network is shared with the virtual resources. Virtualization key features. We shall now have a deeper look on VM features like partitioning, VM isolation, VM encapsulation, and hardware independent. Let's learn more about each virtualization key features one by one in the coming slides. Partitioning. Now, have a look at what is partitioning. Multiple VMs with homo and heterogeneous OS running on a single physical server. It utilizes the physical resources optimally. It enables dynamic provisioning or deprovisioning of resources to the VM. In advance, it also offers clustering of VMs to provide high availability. Isolation. VM isolation offers secure multiplexing, strong guarantees, and performance isolation. As we run multiple VMs on a single physical host. There is proper isolation of the processor and memory. It guarantees strong isolation that prevents all VMs from an infected VM. Mandate for a secure and reliable environment. Through hardware abstraction, each VM is sufficiently separated, independent from the operations and activities of other VMs. Faults in a VM are contained within it, which ensures high levels of security and availability of other VMs. Encapsulation. VM encapsulation means the entire VM is managed as a file with OS applications and data within it. VMs can be captured on the FLY as periodic snapshots or clones and restored to point in time. Snapshots help in rapid system provisioning, backup, and remote mirroring. It also offers easy content distribution as pre-configured apps and virtual appliances. Hardware independent. The underlying physical hardware layer is hidden by the virtualization layer, and hence it becomes hardware independent. Run any heterogeneous OS on any server without modification. The VM once created can run anywhere and can be migrated from one host to the other. No vendor lock-in. Next is about the different virtualization approaches. Server virtualization. Coming to the virtualization approaches, there are 4 types of approaches. OS virtualization, para-virtualization, full virtualization, and hybrid virtualization. Full virtualization is further classified as software-assisted full virtualization and hardware-assisted full virtualization. Hardware-assisted full virtualization is about the different type of hypervisors. Type 1, bare metal hypervisors, and Type 2, hosted hypervisors. Software-assisted full virtualization is about binary translation. Next is about the different virtualization approaches. OS virtualization is a server virtualization technology or an operating system OS paradigm in which the kernel allows the existence of multiple isolated user space instances called containers. A container is a standard unit of software that packages up code and all its dependencies to run an application reliably in any computing environment. Tools include LXC containers, Docker, Zones, Solaris, virtual private servers, OpenVZ, Jails, CRUD, FreeBSD.